Anyway, so we're going to pick back up with chapter 14 today. Again, we introduced this content on Friday, and we're talking now about confidence intervals, and this is kind of one of the two major things that we'll talk about in this class, that of confidence intervals, and the other one we'll get to in the next chapter. So I'll leave a cliffhanger hanging there for you. But remember, now that we're kind of into the meat of the course here, I think we're now doing this thing called inference, which is where we take information from a sample and generalize it to our population of interest. And just, I think we're about middle of page 3 of chapter 14 notes right now. I'm giving a quick recap, and then we'll jump in there. I'll give you a heads up when we're there. But just remembering where we're at. So again, we're going to estimate mu, which is our population, something about our population, and estimate it with x bar, which is the information So we're going to take information from our sample x bar, and we're going to use that to estimate mu, which is our population mean. We had a big long discussion on Friday about a number of things, and kind of the main point of that was that instead of using just a single number, so instead of just estimating mu with the sample mean x bar, we're going to give a range of values for estimates. So we're going to give that's this idea of a confidence interval that we're talking about here. We're going to estimate mu with an interval rather than just a single value, because that will give us some more confidence that our answer might actually be correct. So this is kind of the main idea of the chapter, and then we're filling in details on kind of understanding how to give this interval, how to find this interval to estimate mu, and kind of figuring out what it means. So what we got to right at the end of the lecture on Friday was our formula here. So that if we have looking at the second bullet point there, if we have a simple random sample from our population that has some unknown mean mu, but that we do for now know what the standard deviation is, we can find a confidence interval for mu. So here, this is the estimate that we'll give to estimate mu. And this form here is we have an estimate, which is x bar, and we're adding and subtracting on a margin of error. So this is kind of like that's our wiggle room, right? So instead of giving just a single number x bar, we're going to give an interval, we're going to give a range of values, and here's what that range of values is. So we're going to take our estimate, then we're going to add and subtract something onto it to give ourselves a better estimate of what the population mean might actually be. So that's the formula that you want to start putting into your brain. And so the one thing that we haven't made note about on here, again, x bar is our sample mean, sigma is our population standard deviation, which we're assuming we know now, and we'll come back to that issue later. That's kind of a limiting assumption. N is our sample size, and then this z star thing is the one kind of new thing that we have going on here, and this is our critical value, and whatever that is, that will tell us how much confidence we can have in this estimate. So that's the formula, and we'll hit on this a little bit more. So the z star tells us something about the confidence level. So again, remember, we're giving an interval to estimate mu we're giving a range of values instead of just a single value, so that we can have some more confidence in our estimate. And just reminding you here what that confidence level C is called. So again, we'll have things like a 95% confidence interval, a 99% confidence interval, kind of varying numbers of percents there. And just a key note that the confidence level doesn't tell us anything about the probability of the event containing the interval. It's telling us about the success. It's more of a success rate, or telling us about the process. So you don't need to worry too much about that, but just pay very close attention when we work through some examples and give interpretations, because there's a very specific way to interpret these things and a very easy way to misinterpret them. So we'll look through some examples of that, but just to keep that in mind. So just remind you where we get these z star values. and that comes from, again, we assumed that our population was a normal distribution, so that our sample mean, we know from chapter 11, also has a normal distribution, and so we can use the same tricks that we've been using all along. And so what Z star will tell us, if we want a 95% confidence interval, and that will correspond to, say, 95% of the area being in between plus and minus Z star of the normal distribution there. So I gave you these three sort of standard values, and we're still reviewing some things. We'll get on to some new material in just a second here. Again, sort of the usual confidence levels that we have are 90%, 95%, 99%. And the critical value, the Z star, that you want to use for each of these confidence levels are these three numbers, and they are given in your notes. Went through this kind of quickly on Friday, so I wanted to just quickly show you where does, say, for example, 1.645 come from. So if I want 90% confidence interval, why do I get a 1.645 there? And the key here is that we can use this normal distribution here. So centered at 0. So I want to find this number and this number such that this area in here is 0.90 or 90%. So that's so just showing you how I'm getting 1.645 here. Look, going back to that diagram, remember we want if we want a 90% confidence interval, we want to find plus and minus some value such that they contain 90% of that normal curve there. So if I want 90% in between there, what is for example, what is this area down here going to equal? I think I heard it. 5%, right? So if I have 90% in between, that means I have 10% out there in the tails. So this is going to be 0.05. This is going to be 0.05. And so now we're kind of back in the boat that we were in back in chapter 3 again. Of we have a probability and we want to know what the corresponding z-score is. So again, if we want to figure out if we want this area to be 0.05, we need to find the z-score that corresponds to that. So I can go back to my table. This is my table A. You guys know what this looks like very well by now, and I can search around in here until I find the right number, which is, so I can find, again, I wanted 0.05 was the probability in the tail that I wanted, and so it's going to fall kind of right in between these two. So this corresponds to negative 1.6, and then we can pretend there's a 0.045 column in there, since it's right in between those two numbers. So I come here, I find what the z-score is, and I can go back and fill that in. So that means that this number is negative 1.645, and this number is positive 1.645. So those are that's how I got, and I could do the same thing. If I wanted to find a 95% confidence interval, I need 95% of the area in between plus and minus some value. And if I do the same type of calculation, I would get 1.96. If I wanted 99%, I would find 2.576 would be my plus and minus z value there that I would want to use. So in general, we'll ask you just to use, so the homework problem might say give a 95% confidence interval for blah blah blah, whatever we're talking about. In which case you can use these standard values, but if you had to find, say, I don't know, it'd be weird, but if we ask you to give an 80% confidence interval, then you would know what to do, right? You would draw on your normal curve here. Here's z, here's 0. We would want to find out this number and this number such that in here was 0.800. And you could find what those question marks were based on the same thing that we did. Going to the table, so if there's 80% in there, then in here is 10% of the area, and you could find the corresponding z-score and all that good stuff. So again, in general, we'll ask you to use just these three confidence levels, 90, 95, 99, but if you had to do something else, that's the way that you would go about doing it. Any questions on this so far, or anything else that we covered on Friday? You okay so far? All right. Well, let's do a few more examples here. I think we're maybe just about ready to do some more examples. Just remind you here that that's the formula we're going to be using. It's the same slide as before. But as we're moving now into doing some examples, it becomes a little bit more important for us to kind of formalize the process here of how we answer these questions. And so this something that the book calls the four-step process, which is a great outline, sort of a great template for you to use when you're thinking about how to solve these problems. So, when we're working through examples in class here, well, here we're in chapter 14, so we're going to do this. Or maybe we're in chapter 11, we're going to do this. And whatever chapter, it's kind of very clear as to what we're doing, but as you move into your homework problems and maybe on an exam, thinking about what exactly am I doing here, this four-step process will be kind of the way to go. So we'll go through this very, very carefully initially, and I would encourage you to use this as you're working on problems, but we'll kind of move through these things more and more quickly. But in any case, the four steps are that we want to state the problem that we're interested in. So what is the actual question that we're being asked, and what am I actually doing here? So we're going to state the problem, then we want to plan, thinking about what is the question asking, what do I need to do to answer this question. Then we can actually solve the problem. We can do maybe check our conditions and calculate, do our formulas, all the mathematical stuff there. And then finally we want to conclude, returning to the question and describing exactly what we've done. And so again, like I said, we'll get a little bit more laid back with this as we go on, but kind of the main point is that it's very important to think about what it is that you want to do. Check to make sure that you can actually do it using the methods that we're looking at. So that's checking conditions and all those things. Actually doing the calculations, and then finally communicating your results in context. And I'm going to harp on number 4. That's probably the most important one up here, is being able to, you need to do the other things correctly, obviously, but being able to communicate your results is extremely important in statistics and in the world, right? So we'll get some practice here on that. So I'll get off my high horse and we'll do an example here. So we're going to go back to this. We'll have 2 examples here, I think, or maybe this is the only one. But kind of going back to the same example we saw at the beginning of the chapter, and we'll now formalize kind of what we've done and show you exactly how to answer these kinds of questions. So the information that we're given here in this example is that we're looking at commute times, and we're told that in 2011 these commute times followed a normal distribution that has this standard deviation of 10 minutes. We take a random sample of 75 people, and we find that their average commute time in 2011 is 50 minutes. And then what we want to do is give a 90% confidence interval for the average commute time in 2011. All right, so again, here we're going to go through this 4-step process very formally, just to say here's exactly what we're going to do. And maybe before I do that, let's pick out the information that we've been given. So we've been given a few numbers here, and let's practice picking out what each of these things are. So again, this should be pretty straightforward. What is this 10 here that we have going on in symbols, or what is that? Right. So that's my population standard deviation. Right. So it's corresponding to the all commute times in 2011. And again, we're assuming for now that we know what that is, and we'll come back to that since that's a bad assumption, but we'll come back to that later. So the next number is 75. What is 75? Right, that's our sample size. That's n. And finally, it looks like we have a 50 going on here. What's that number? X bar. Yes, exactly. That's the mean. That's the mean from our sample. So we took a sample of 75 people. We found that their average commute time there is 50. So in any case, let's move on here with the 4-step process. So first first step is to state. So again, and here's very simply kind of restating the question again is what is the practical question that we want to that requires estimating a parameter. So here we want to we would like to know how long the true average time was for all Americans back in 2011. So again, the question's asking us for a 90% confidence interval, but keep in mind what we're really trying to do here is we'd sort of like to know how long the sort of the true average commute time was for everybody. So again, if we were able to ask everybody, we could find this out, but we can't. So, but that's kind of practically speaking, that's the question that we're trying to answer here. And again, this one's obvious because we're in chapter 14 here. But the way that we're going to do that, our plan is that we will estimate the population average commute time with a 90% confidence interval. Sorry, that's getting small at the bottom. So again, we want to know what that population average commute time was, and so to do that, we're going to estimate that the population average commute time with a 90% confidence interval. So again, there's our practical problem, and here's kind of our plan, or how we're going to go about answering that question that we're interested in. Again, being very careful about this for now. So, okay, we've stated our problem. We've planned kind of what we want to do. So now we actually want to solve. We want to figure out what that confidence interval is. So remember, under the solve step, that means that's actually two phases in here. So maybe it should be a 5-step process. I don't know. But first, we need to check the conditions to make sure that we can use this formula that we have, and then we actually need to calculate the confidence interval. So what we're going to do is we're going to go back to, if you look back to the first page of chapter 14, we had those 3 simple conditions about doing inference for a population mean. We discussed that these were kind of unreasonable, but for now those are the conditions that we want to check, and we'll go back to some more realistic conditions in a minute. So first, what we want to do is check conditions. And my 3 conditions here in chapter 14 are, do I have a random sample? Is the population normal? And do we know the population standard deviation sigma? So this is coming from that first page. Then when you're doing a problem from chapter 14, here's the conditions you want to check. And again, we talked about why these might be kind of silly assumptions. But anyway, we're going to go with them for now, and we'll come back to that. Come back to assessing those later. So do we have a random sample here? Yes, right? See lots of nodding heads. It's stated in the problem. So we're good there. Is the population normal? Do we have a normal population? Again, yes. It's stated in the problem again. These are not going to be very exciting here. And finally, do we know sigma? Well, yes, of course we do. Again, it's given in the problem. So we're all good to go here. Each one of these things has checked out, and we can go ahead and use our calculation that or our formula that we have here. So now we can actually write down what this is again. So our 90% confidence interval we want to find. Again, is x bar plus or minus z star times sigma over the square root of n. And for me, it kind of helps me to make a list of what's the information that I have, what do I need to find out, and then I can go ahead and plug all these things in here. So I need to know what x bar is, I need to know what z star is, I need to know what sigma is, and I need to know what n is. So again, from the example, we were given some of these things, right? X bar was, we picked that out, that was 50. That's the average from our sample. We had 75 people in our sample, and we found that that sigma was equal to 10. So the one thing that I have left to figure out here is what is z star. So if I want a 90% confidence interval, what should z star be? Yes, exactly right. It's the 1.645 that we had earlier. All right, so again, there's our formula. There's everything that we need, so we can go ahead and just plug these numbers in and see what we get. So our x bar is 50 plus or minus 1.645 times sigma, which is 10, over the square root of 75, which is the same as 50 plus or minus 1.9. So therefore our 90% confidence interval is 48.1 to 51.9 minutes. So again, just plugging the information that I have into the formula. I get my confidence interval is 48.1 to 51.9 minutes. So you can also write a confidence interval as something like 48.1 and 51.9. If you want to write it that way, that's fine. Writing it out 48.1 to 51.9 minutes is good too. Whatever's makes sense to you. All right, so again, now I've sort of solved my question, right? I checked my conditions and then actually did the calculations. Final step here is to, and a question came in, I'll get to that in just a second. Final question is to conclude, or sort of state in context what we got. So again, our 90% confidence interval, 90% CI was 48.1 to 51.9 minutes. That's what we got from step 3. So again, we have a very specific way we want to interpret this. So how we'll say this is that we are 90% confident that the mean commute time, for all Americans let's say all American workers in 2011 was between 48.1 and 51.9 minutes. So again, the way we would interpret that confidence interval is that we are 90% confident that the mean commute time for all American workers in 2011, that's what we're trying to say something about. So we're 90% confident that that is between 48.1 and 51.9 minutes. And again, I would encourage you to use this as a template. So again, fill in what your confidence level is. So we're blank % confident, and then that the mean commute time for all American workers in 2011. So that's mu, right? That's our population mean, and then say what the two numbers were between, or what the two numbers of your confidence interval were. So it's very important to go past calculating what the confidence interval is and say what it means. And here's what it means. Questions or comments, or is everyone okay with what we're doing here? So again, instead of giving just a single number to estimate this mean commute time for all American workers in 2011, we're going to do a range of values. And here we found that range of values, and we can attach a level of confidence to it. So we're 90% confident. We're pretty confident that the true mean is in that interval. So the question just came in on a test or exam: would we have to solve and prove that 90% confidence is 1.645, etc., or can you just go from memory? You can just go from memory. You don't need to prove that 1.96 corresponds to 95% confidence. And in the past, I'm not sure how Dr. Baker will do it, but I think we might even give you those 3 critical values that we had up here earlier. But in any case, it's as you do lots of these problems, it'll start to you won't be able to get those numbers out of your head. So, but you won't need to prove that those are the right numbers as long as you select the one that corresponds to the right confidence level. All right. So let's so there's our first way through this example. So as sort of a follow up here, suppose now we wanted so we just found a 90% confidence interval. Suppose we wanted a 99% confidence interval for the average commute time in 2011. So I'm not going to do that whole song and dance again. You could fill in the same exact steps apply here. We just want a 99% confidence interval. So again, we want x bar plus or minus z star times sigma over the square root of n. For 99% confidence, what's my z star going to be? Looking back in your notes. Thank you, Alyssa. 2.576. So now I can just fill in the same numbers. My sample mean was 50 plus or minus 2.576 times 10 over the square root of 75, which is 50 plus or minus approximately 3.0, which is 47 to 53 minutes. And then we can say, again, using our sort of standard template there, so what we would say is we are 99% confident that the mean commute time for all Americans in 2011 was between now 47 and 53 minutes. So doing the exact same thing that we just did. So if we go from a 90% confidence interval to a 99% confidence interval, really the only thing that changes is what our z star is, and then of course we'll fill in that we're now 99% confident and instead of 90% confident. So same thing we did before there, just kind of again practicing doing these calculations. So question for you here. So again, I started out with having 90% confidence, and then I increased my confidence. I'm now more confident that my interval is correct. I'm now more confident that I have the right interval there. So a question for you: as my confidence level increases, what happens to the width of my confidence interval? So does it get narrower, stay the same, or get wider? How many think it gets narrower? Choice A. How many think it stays exactly the same? And how many want to go with C, that it gets wider? Exactly right. So you guys can look at those two intervals that we calculated, and we see that the second one is indeed wider. So choice C is correct. So as your confidence increases, as your confidence increases, you're going to have to make your interval wider. And I think this, I don't know if we have any football fans in here, but if you pretend that you're a field goal kicker, and you want to be, and so pretend you're kicking a field goal. So I couldn't kick a field goal, but let's pretend that we're in that boat. Say we're kicking a 20-yard field goal, and what would need to happen to those field goal posts if I want to be more confident that I'm going to make that field goal? They're going to need to get wider, right? So think about field goal posts are narrow. It's going to be hard for me to make that field goal, so I'm not going to have very much confidence. But if my field goal posts get really wide, it's going to be more likely I'm going to be more confident in my ability to make that field goal. So same kind of an analogy goes here. So we'll just put a little thinking about kicking a field goal. That if you want your confidence to be larger, you're going to have to make your interval wider. And again, Z star went from being 1.645 up to 2.576. So you're multiplying, you're adding and subtracting more, which means your interval gets wider there. So that's the first important conceptual thing here. Next, so again, same question. Now suppose that the random sample we had was 300 people. So now we're going to let n equal 300. Suppose we had 300 people in our sample, but we found the same average commute times. We still found an average of 50. And again, let's go back to that 90% confidence interval that we did sort of the whole way through. So now x bar plus or minus z star times sigma over the square root of n. Now this is, again, our same sample average plus or minus. Z star is going to be 1.645 times the standard deviation divided by the square root of 300. So I'm just saying my sample went from 75 up to 300. So what this gives me now is that I have 50 plus or minus 0.95 or 49.05 to 50.95 minutes. And I'll let you practice writing down what the interpretation there is. I'm not going to do that a third time. So same thing that we did before, but now we're just saying we have more people in our sample. So thinking about how that affects my confidence interval here. So similar question as before. So now as my sample size gets bigger, what happens to my confidence interval? Anybody want to yell it out? Gets narrower, right? You can just look at that and see that that's true. And that is true in general. So again, because remember the margin of error is the z star times sigma divided by the square root of n. So as n gets bigger, means that the margin of error gets smaller. So as you divide by a bigger and bigger number, or the square root of a bigger and bigger number, that margin of error is going to get smaller. And this kind of goes back to the idea we saw in Chapter 11 that that large samples are less variable than small samples. So same idea sort of holds here, that as we take more people in our sample, that margin of error is going to get smaller. We'll have less variation in our sample. All right, so that brings us to the end, I think, of chapter 14. Any final questions you guys can think of before we move on a little bit? Okay for now. So again, this is our introduction to confidence intervals, and this is a very, very important thing. I guarantee you that all of you will see a confidence interval at some point later in your life. You might not have to calculate one, but I guarantee you that you will see one. And this is kind of the idea, that we're, instead of using just one number to estimate something, we're using a range of values, and then kind of thinking about what the interpretation there is. So thinking about what my confidence level says about, think about the confidence level tells me sort of how good I think that estimate is. And so here in chapter 14, we've made some very sort of limiting assumptions, like we talked about. We'll come back to those assumptions, I think, in chapter 18. We'll get back to that. But we're going to leave confidence intervals for now and move on to chapter 15. So if we're all set, I think I sent around those notes yesterday. Sorry, these are coming at you a little late, but and again, I posted. So there's a version of these notes posted sort of under the general Carmen content page. Under the section that's specific to this class, I posted a version that's slightly more filled in. So there's a little less for you to fill in. They're more like sort of what we did at the beginning of the course. Anyway, I also emailed those to you. Hopefully you have those. So here in chapter 15, we're looking at something called tests of significance, and sort of introducing what these things are as well. So let's see if we can get through a little bit of the definitions here in this chapter before we finish up for today. So back in chapters 10 and 12, when we were looking at probability, which you guys are doing now, we used information about a population to answer questions about our sample. So we were told something like, for example, that if 20% of all people are smokers, what's the probability that in a random sample of 2 people we get both of them smokers, or something like that. So that was kind of the overall idea there. And so now we want to kind of go the other way around, right? So like we did in chapter 14, we're going to kind of do the same thing here. We're going to again use information from our sample to answer questions about the population. Same deal here. So what we saw in chapter 14, again, this is on the same day now, so it doesn't need as much of a refresher. But if to estimate a population parameter, again, we used a confidence interval. So again, that idea, instead of using a single value to estimate the parameter, we're going to use a range of values. So that's one side of the statistics coin. The other side here is what we're looking at in this chapter. It's this idea of a hypothesis test. So in the confidence interval, we're trying to estimate something about the population mean, or something like that. The other main way that you guys will maybe be using statistics in your later courses is this idea of a hypothesis test, in which we want to assess the evidence provided by our data about some claim about the population parameter. So now we're going to do something like, if I tell you that the average commute time in 2011 was I don't know, 52 minutes, what we're going to do in this chapter is you're going to assess the evidence for that claim. So is what I told you correct, or is it not correct? That's kind of the direction we're going here in this chapter. So confidence intervals was chapter 14. Here, the other main thing that we'll be looking at is this notion of a hypothesis test. So as sort of a motivating example here, we're going to look at this screen time example. So we all love staring at screens, don't we? I know I do. So here in this example, screen time is I'm doing it right now actually, is the amount of time that a child watches television in front of a computer, smartphone, all these things. So anyway, screen time is believed to be linked to other ills in children. So a variety of problems there. And a recent study that we did indicated that the average screen time for children under 12 was 6.1 hours. So we're not told a lot of information, but just this recent study found that the average screen time was about 6.1 hours. And suppose that you have a 10-year-old cousin Gavin, and you're sort of concerned about how much time he's spending looking at a screen. And when you're thinking about when you're wondering about his screen time, there's sort of maybe two questions that you could ask yourself, or two situations that you might result in. First of all, that the amount of time that he looks at screens is not different from that of other children under 12. So it's the same as what other under 12 children have. Or the other thing that you could conclude is that it is different. It's different in some way from that of other children under 12. So if I'm concerned about his screen time and I want to see how he compares to other children, either I will conclude that it is not different from other children, or that it is different from other children. So those are my two possible hypotheses, and these have names actually. These are the kind of hypotheses that we'll be looking at in this class. So again, like I said, the idea is that we're going to assess the evidence for a claim. So I'm gonna tell you something like Gavin's screen time is equal to some amount, or that it's equal to that of other children, and you'll be able to say, well, yes, it is different, or no, it is not. No, it is not different. So anyway, these two hypotheses. The first one is called the null hypothesis. We're going to denote H sub 0, or that's our null hypothesis. And that is the claim that we're sort of interested in testing about the population parameter that I'm looking at. So whatever that parameter might be. Again, keeping that the test is designed to assess the strength of the evidence against the null hypothesis. So usually the null hypothesis will say something that there's no difference, or there's no effect, or sort of like in our previous example, there's no difference between Gavin's screen time and the other children. So that's my null hypothesis. Sort of the key thing here is that I'm assuming that there is maybe no difference. The other choice there, my alternative hypothesis, which I denote with an H with a little a. You also might see H with a capital A, or you might even see a 1 there. We'll stick with the A's, but if you see an H1, that also corresponds to the alternative hypothesis. And that's sort of saying the other thing. And so again, that's saying that if the null hypothesis says there is no difference, then the alternative hypothesis says that there is a difference. And my alternative hypothesis is sort of what I'm trying to find evidence for. So I'm trying to show that if I'm trying to show that there is a difference, that's what I'll say here in my alternative hypothesis. So again, what this is saying is that if the null hypothesis says there is no difference, then what my alternative is saying is that there is a difference. Sort of my two options there. Either there is no difference, or there is a difference. And so with that statement of there is a difference, there's a couple ways I can say that there is a difference. I can have, and this leads to some more definitions. So I can either have a one-sided alternative hypothesis or a two-sided alternative hypothesis. So again, the alternative hypothesis HA says there is a difference. But then I can either go having a one-sided alternative, which says that difference means that that's bigger than or smaller than. I'm only concerned about one of those cases. And then two-sided, two-sided will be just the case where I don't care if it's bigger or smaller. I just want to show that it is indeed different. So whatever it is I'm trying to make a statement about, one-sided, I would say that no, that number is actually bigger than whatever my sort of whatever I tell you that the value is, or smaller than. Two-sided just means that it's different from whatever I said in the null hypothesis. So going back to our example here, the screen time example, again, our two possible hypotheses here are that, again, that the screen time is not different from that of other children, and then the other thing is that it is different from other children. So the question that I want to ask now is kind of thinking about that one-sided versus two-sided. Do I have a one-sided or a two-sided alternative hypothesis? So again, so let me quickly write down the parameter I'm interested in. Parameter. Here again, I'm trying to say something about Gavin's screen time, right? So my parameter is going to be mu, which is the mean. Well, let's say the mean daily amount of screen time for Gavin. So again, my alternative hypothesis will be saying that there is some difference. So here, am I interested in showing if Gavin's screen time is more than or less than, or do I just want to know if it's different? Well, you can kind of pick it out. I'm just interested that it's different. I'm not saying Gavin's amount of screen time is greater than that of other children. I'm not saying is Gavin's screen time less than that of other children. I'm just wondering, is it different? So this is going to be a two-sided alternative hypothesis. Because we just want to know if is Gavin's screen time different from. So we're not concerned if it's more than other children or less than other children. We just want to know, is it different than that of other children? All right. So here's sort of our, just sort of intuitively, here's our two hypotheses. Let's go ahead and write down exactly what, kind of in our formal notation, what my null and alternative hypotheses are for this example. So we're going to use our notation. Remember that mu, again, we're going to say is Gavin's daily average screen time. So my null hypothesis again is H0. Put a colon there. And again, looking at the previous page, we said the null hypothesis we want to is a statement of there being no effect or no difference. And so that was number one of our possible hypotheses. We said that Gavin's average daily screen time was the same as that, or was not different from that of other children. So we can say that mu equals 6.1. So that, and in words, just remind you, this is not different from other children, which we found was 6.1 hours. And that's just the information we had from the study. A recent study we said found that children under 12 have an average daily screen time of 6 hours. I hope that's not daily, but it probably is. That's a lot of hours. Anyways, that's my null hypothesis, which says that there is no difference. So again, I'm saying Gavin's average screen time is the same as other children. My alternative hypothesis here is sort of, again, the definition that we had is that it's the claim that we're trying to find evidence for. So again, is Gavin's average screen time different from that of other children? So we have simply that mu is different from 6.1. So it could either be less than that of other children, it could be more than that of other children. We just want to know, is it different from? So this is saying that Gavin's time is different from other children. So, yes?
Do you also accept saying that it's larger than or smaller than?
Yeah. Sure, yeah. So the question was, would I accept saying that it's either larger than or smaller than? Absolutely. That's saying the same thing. That's just fine. So again, kind of a simple example here, but there's setting up these claims that I'm interested in testing. So if I want to know something about Gavin's average screen time, how does that compare to other children? This is kind of how I set it up, and where we'll go next is being able to make a decision here. So which one of these things is true? So this is a good place to stop. I think I'm out of time anyway. Thank you guys so much for being here. We'll resume this discussion on Friday. Have a good rest of the Wednesday. Hopefully it won't be raining as hard on Friday.